Okay, as our next topic, we are going to talk about eigenvalues and eigenvectors. Okay, now eigenvectors and eigenvalues, they are helpful for transformations. Okay, linear transformations, and we also have another topic called singular value decomposition. Okay, that also is helpful in compression. Okay, compression of the images, etc. We'll look at these two topics and we'll be done with linear algebra. Okay, so eigenvector, you have to understand first that when you do a transformation, and transformation also, in one of our previous classes we already saw some of the linear transformations, matrix transformations, right? And also vector transformations we saw. What happens is when you multiply a vector, um, yeah, this is the transformation. So when you multiply a vector with certain scalar value, okay, it gets stretched, right? Same thing happens for the matrix. Okay, even matrix, uh, it gets stretched, basically that's all it is. And when you add a value to a matrix, okay, um, s- so here ideally this should have been addition because we are adding here. So this is incorrectly represented in the image. um, okay, this has to be addition. Okay, if I execute, do a run all here. So if you execute that, you will get the transformation done on the file, and that transformation happens to be addition. So basically what we are saying is, if you multiply certain scalar value to a vector, it gets stretched, it gets transformed, right? Stretch, transformation, both are same. And if you add it, it not only gets stretched, it also changes its position. Okay, now the same concept we are taking, okay, for eigenvalues and eigenvectors. Essentially what we are saying is, you take a vector, okay, let x be some vector here. Okay, um, in this equation ax is equal to lambda x, let x be, what we are saying is, let x be a vector and a be a matrix, some matrix, some square matrix. And when you multiply a matrix to a vector, it turns out some transformations happen on that vector. It gets stretched, it gets moved, it moves from one place to another. Some it changes the direction, some transformations happen. Okay, when you do this multiplication, it turns out the same end result that you get after multiplying that matrix to that vector can also be obtained by just doing a scalar multiplication to that vector. Lambda here is some scalar value, some L value, some 1 2 3 5 10, whatever it is, 1 by 2, whatever it is, some scalar value multiplied to that vector has the same result as the entire matrix multiplied to that vector. Okay, now these lambda scalar value that yielded the same result as a matrix transformation, matrix vector product transformation, is called as eigenvalue. Okay, and the vector is called as eigenvector. Okay, did you understand? When you do the transformation to a vector, let v1 be my vector, some vector, what we are saying is, okay, in this case, when what we are saying is, to this vector v1, if you multiply this L value or lambda here, L value is same as lambda value, some lambda value, the transformation that you have obtained is same as this transformation you would have obtained when you multiply the entire matrix to that vector. Okay, if you multiply a matrix to a vector, whatever the transformation you see is same as the transformation obtained after multiplying the scalar value. And this doesn't happen to all the vectors. Okay, it happens to only square matrices and square vector. Okay, some certain values have to be determined. The matrix that you are multiplying it has to be a n by n matrix. Okay, and it should be a, and x should be a non-zero vector. Only then this relationship is established. In that scenario, we call lambda as eigenvalue and x as eigenvector. Is this clear? Did you understand? This we are gonna reuse in a lot of places. So is this definition, and at least are you able to understand what we are saying here? Okay, all right. So you can calculate for any, let A be a matrix here. Okay, it could be any matrix. Randomly I have taken the values here. Okay, so if it turns out to be a uh, how the way how you calculate if it is a eigenvector is by subtracting a minus scalar into identity matrix. If you subtract this and multiply with this vector, you should get 0. Okay, this is a constant definition. Okay, and here columns should be linearly dependent. Okay, we just understood what is meant by linear dependency and linear independency. Two lines or two um system of linear equations are said to be linearly dependent if they coincide. Okay, or in other words, a matrix, a columns or the rows of a matrix are said to be linearly dependent if they have zeros in them. Okay, so that is what it is. So we are saying eigenvector should be non-zero vector, then this will exhibit certain properties, and those properties are nothing but column should be linearly dependent, which means some of the columns should have zero values, and a minus lambda I, um, its rank should be less than the highest value of row or columns. Okay, and a minus xi is not invertible, means you don't have inverse matrix to it, and determinant of a minus lambda I should be 0. So these are some characteristics of eigenvectors and eigenvalues. And where do we use these eigenvectors? What are the applications is, you can use it in lot of places. May it be doing a page ranking. Okay, may it be compressing the data, mostly for compressing the data in our case, because we are doing data analysis. We will be compressing the data, and why we need to compress the data also I will explain you. Okay, to compress the data you will be using eigenvectors. And not only that, to google, how this is how google previously used to do the pages. It used to store the page rankings using, by calculating the eigenvectors. Okay, and not only that, so even there are certain things like HMMs. Okay, hidden Markov um, models. Okay, so there also you would use eigenvectors. Okay, Markov processes. Okay, where they call it Markov process, but they are essentially called as HMMs, hidden Markov models. So there also you make use of eigenvalues and eigenvectors. PCA calculations, principal component analysis you will do. Why you will do, where you will do, how you will do, so everything I will explain in data analysis. But just understand these eigenvectors and eigen value calculations, they are used in multiple places. Mainly they help us in compressing the data. Okay, and they also not only compress the data but also in a sense that they kind of transform the data. I should use the word transform instead of compress. Okay, so they transform the data in such a way that uh, lot of dimensions are reduced. Okay, that way I was saying compressing the data. Anyway, so in various places they are used, and let's look at how they are calculated. what they look like and how they are calculated, we will look at. Okay, so in our calculation I have taken a matrix A. Now to this matrix, all you have to do is call again the numpy function, and for numpy there already exists a inbuilt linear algebra function for that. um, so all you have to do is, okay, so if this is your A, I have just generated some random A. So for this A, you just have to do A dot, sorry, np dot linear algebra, okay, dot eigen. Okay, so you have Eigen, and you can pass the matrix. If you look at what Eig is doing, it is computing both values and vectors. Okay, both the things it's generating at the one same time. So that's why you have, when you assign the value, you have to always assign eigen values first and eigen vector first, and then assign. Okay, and then you can print, you can calculate, and then you can print eigen value. Okay, this is your eigen value for that matrix, and eigen eigenvector. So this is what the eigenvector looks like. There is always real component and imaginary component in the matrix. Don't worry about the imaginary one. So just understand that this matrix, see, the original values were 2, -1, 3. Look at the later on values in the vector. So they have changed, right? Now let's try to establish this relationship. um, A minus lambda 1. So where is that? Determinant of A minus lambda I equals to 0. So here determinant is nothing but lin all dot det. This is our determinant. Determinant of what we have to calculate? Determinant of A. Determinant of A. A is nothing but our original matrix. So I will pass as is determinant of A minus lambda. Okay, determinant of complete thing. Okay, it has to be a determinant of complete thing. Okay, determinant of A, inside the bracket you have to pass minus lambda. What is our lambda? Eigenvalue. Eigenvalue. Identity matrix you want. Okay, into dot product you have to calculate. Np dot I of 3. Okay, um, let's look at np dot I of 3. Okay, so np dot determinant of A minus lambda I equals to 0. Okay, have I taken the same example? No, I have not taken the same example. Okay, let me change the value of A, because it's not calculating for the one we want it to calculate to. It's 1 comma 0 comma 0, and then comma, next is 1 comma 0 comma 1. Okay, and then 2 comma minus 2 comma 3. Okay, this is our A. Eigenvalue, calculate, you get 211. Eigenvector looks something like this. Okay, 0 point. Okay, so minus 3.0. Determinant of um, this is fine. 100 101. 2 minus 2 3. Okay, 211 is correct. Okay, and that value is also correct. Np dot data. First, let's calculate this instead. Hmm. This is an array. Okay. Why is this not equal to 0? Okay. Anyway, so for this particular matrix, it's not coming as 0. But let me calculate on for the same matrix. Let me calculate on the tool. Maybe then we will see compare the results. 100 101. Okay, 100 101. 2 minus 2 3. So I just entered these values. Okay, just before the class started. So when you calculate, there exists eigenvectors, right? So eigenvectors, if you notice, lambda 1 is 1, lambda again another one is, these are eigenvectors. 1 1 0 minus 1. Okay, so 0 1 by 2 1, maybe 1 by 2, that is why it's represented as 0 0.5. Okay, so the calculations are being shown here, how it is calculating. Determinant of a minus lambda I is being calculated. Ultimately you will get 0 only. Okay, we will have to check why in our case it's not giving 0, but anyway. So if you notice the calculations, there are too many calculations. So finally you will get these results. Don't worry about how it is calculating, just notice that this lambda 1 lambda, whatever the different values of lambdas are, so these lambdas are scalar values. When you multiply it to your original vector, um, you will get the same transformations. And uh, to picturize it, it is little tedious, but we will see. I will try to show you what it means. Okay, so so here let v be some vector. Okay, and to that first we will try to multiply with matrix A and lambda. uh, in this plot they have already calculated certain vectors. Okay, one vector, if you notice, what they are trying to map a real world scenario where a aircraft flies from certain cities. From Perth, if or there is a city called Perth. Okay, if it flies from to and fro Perth, then it is placed at p of 0 comma 0. Okay, it is p of 0 comma 0. This is Perth. Okay, this is Brisbane. Okay, this is another city, Cairns, I don't know how to pronounce it. Cairns. Okay, and this is Goa. Okay, so four cities are represented. Now for these four cities, Brisbane is at certain value, another city is another value, Goa, and another one is also represented, W is here. Where is this oil well? Okay, now uh, so eigenvectors, if you talk about Brisbane, here skew B stands for Brisbane, C stands for Cairns. If you notice, Brisbane is this point B, pink line, and Cairn is this point C. So these two vectors are already plotted. From Perth, a flight can go from Perth to Brisbane. Flight can go from Perth to uh, Cairns. Okay. Now, if I talk about Brisbane, only Brisbane. Okay. Now, eigenvector is the vector. Notice what is happening. Eigenvector is the vector upon transforming, it does not change. Or in other words, the transformation that it's going to have is only a scalar multiplication, which means the maximum transformation you can see is stretching. Notice how it is stretching in the same line. This line doesn't change. Compare this pink line versus blue line. Blue line can move. See, blue line is actually moving, but B line is only stretching, not moving. Notice? So, in this case, we say the line PB is a, a eigenvector. Eigenvector is a vector that upon transforming, either you do a transformation with a matrix or with a scalar, doesn't matter, both are same. It exhibits a unique property in that it only stretches, it doesn't change. Only the magnitude changes, the direction does not change. See, line PB is still in the same direction. Even PM is a vector, is a eigenvector, if you notice. Okay, but PC is not eigenvector, PG is not eigenvector. Okay, notice in the map, they are moving. PG, PC are moving. They are stretching as well as moving, whereas PB, PM, they are only stretching, not moving. Not moving as in they are not changing the direction anywhere. Such vectors are called as eigenvectors. Okay. Now, how do I use this eigenvector? Where do I use it? Let's just say you have a photo. Okay, although I'm using singular value decomposition here. Okay, but still eigenvectors are applied. So let's just say you have a original image. Okay, what are images? Images are nothing but matrix values. Okay, are vector values, and matrices are nothing but vectors, right? So if I calculate a eigenvector for this image, then no matter how much scaling I do, the image does not change. The vector, only the vector magnitude changes, direction doesn't change. Hence I can either upscale the image or downscale the image, or in other words, I can compress the image. Are you understand, are you with me, are you following what I'm saying? Where did that go? um,
Yes.
you're understanding, right? So
Yeah.
So when we say the image is applied upon by the eigenvector,
mhm.
so what exactly about the image does not change? Will it not change the size of the pixel, like the matrix there?
No, the
Or
entire picture
because
itself doesn't change. Only the, it can increase in size. This image, it's, if you notice,
Mhm,
0 to 800 it is there, right? 0 to 1000 maybe it is there, and here it
mhm,
is 0
mhm.
to 750 or something. It
800.
is there. Yeah,
Yes,
800
yes,
whatever
yes.
value. So you can
Mhm,
increase it to 2000 by 3000 whatever. The image
mhm.
is retained.
Uh, the image is retained means it's uh,
It means,
because
okay, okay, let me show you. uh, Eigen, uh, so all I'm trying to say is, you have a image. Okay, you have
mhm.
certain image. Okay, uh, landscape image. Okay, you take this image. Okay,
Okay, yeah.
okay, this image is there. So now what I'm saying is, first of all, first application of these eigenvectors is compression. Okay, that's what I said, right? So compression means, okay, okay, let me show you this as well, otherwise you, I think we already saw this. Yeah, okay, coming back to this matrix. w- it doesn't matter either whether it is a image or whether it is a tabular data, whether it is a text data, whether it is your voice data, whatever it is, at the end of the day it is all a matrix only. Okay, and matrix can have huge sizes. Okay, like thousands of rows, or sometimes lakhs of rows, crores of rows of data, right? And what happens is, computation is huge. Okay, computational requirement is huge. But what if there was a way for me to retain the entire information as it is by compressing, by decreasing the number of rows? Okay, by decreasing the number of rows, okay, or increasing certain values, decrease, mostly decreasing only. So decreasing the values, I can retain the same information. Then I can save on some computation, no? I can save on computation but retaining the same, mostly the same information, right? So that is what is being applied here. So when you open this image, what you are essentially doing is, see what I'm showing you is scaling now, because I'm using this scaler, you can scale. But eigenvector also does the same thing. Okay, so if I decrease also, the image is the same. Okay, although here the resolution is not changing, but the resolution might change when you apply a PC
Okay,
onto
so
the image.
basically, you mean we mean to say any image which is represented as the matrix
Yeah,
of certain vectors,
yeah.
and for each pixel,
Hmm.
it will have certain value from
Correct,
0 to 255.
correct.
So when we are actually changing this,
Hmm.
even if we are changing the uh, pixel
You're
sizes,
transforming.
like
Yeah,
yeah, when we are actually transforming, so when
yeah,
we are changing the length by width,
right. Yeah.
suppose earlier it was 800 by 600, and we are maybe scaling it up like
Hmm.
2000 by 2000, something like that.
Hmm.
So in that case, will we be changing the uh, the contents of each pixel
Yes.
when we are transforming? Because during the transformation,
Yeah.
will the contents be changed as well? But still, the image,
Yes.
the output of this will remain same.
Yes.
Is it what
Yes.
we mean by here? Okay,
Yes.
okay,
Yes.
thanks.
That is what it is.
Okay,
So
okay, thanks.
I'm showing image because it is easy to picturize, but the same thing is done for tabular data also. It same thing is done for signal processing also. Okay, the same thing is done for basically anything that is represented as matrix. Okay, so this concept we are using, you notice it is decreasing, values are decreasing. Notice that PB. So and compare those values on the right side. See, earlier it was like this, right? Earlier the value was some value here. Notice which value is changing. Okay, so the diagonal, non-diagonal values are changing, right? But this is your vector. Vector is remaining the same. Scaling factors are changing, lambdas are changing. Okay, but the vector is either stretching or decreasing in size, but the information is the same. Okay, if you scaling factor may change. So if each box here represents 1000 or maybe 500 kilometers, okay, and that way if I calculate PB distance is, let's just say 2000 kilometer, okay, 2000 or 3000 kilometer. If I decrease like this, now the scaling has increased, each box now represents some 1000 instead of 500, but the distance still remains the same. PB is still the same 3000, because each box is representing 1000, 1000, 2000, 3000. Did you get now? Did you understand? Okay, anyway, if you don't
Yes, yes,
understand, it's
yes.
fine. But in future, we will again revisit this topic in PCA. Okay, so this is just the visualization part for us to build some intuition. So there are some certain vectors that, okay, they lose their actual values, some don't. Okay, the vectors that don't lose their value, they are called as eigenvectors. And the value by which they get compressed or they get stretched is called as eigenvalue. Okay, this lambda value. Okay, lambda value is nothing but, eigenvalue is nothing but by the factor by which they are changing, that is eigenvalue. Okay, so coming back to this example. Okay, here, I think, Yeah, here we have various eigenvalues. Okay, three different, because it's a 3 by 3 matrix, right? So three different values are there. And eigenvector is also eigenvectors are also calculated. The entire calculation, you don't have to worry much on how it is calculating. Okay, if you are still interested, you can always open this tool and find out, go line by line to understand. But for us, what for especially for data scientists, what you need to remember is eigenvectors can do the transformation and retain the information. Okay, that is all we need to know. Ideally, okay, for in this case the determinant is still not zero. Maybe when it is not zero, then this particular matrix will not exhibit a eigenvector. Okay, so if it is a eigenvector, then this conditions should hold true. Okay, because it is not holding true, maybe this vector, this particular vector that we have taken, or matrix transformation that we are doing, it does not exhibit, um, it does not have proper eigenvalues. Okay, so anyway, um, is you can also understand from here on how they are calculating. Okay, so if you were to go directly by the definitions, so eigenvectors, first of all, they are square matrix, and they don't have, they are non-zero vectors. Okay, when they are multiplied, when you multiply that square matrix with the vector, okay, it is same as though you are multiplying the scalar with the vector. Okay, hence this relationship av equals to lambda v. And um, if you want to um, establish, okay, for because if it is a eigenvector, then there is a condition they hold true, that is a minus lambda I into v equals to 0 should be a zero matrix. Maybe that is what we are missing here, we are missing the v. Okay, or whatever the scenario is. So this condition should be met for a eigenvector, and the value by which these vectors get undergo the transformation, that is called as scalar value, which is eigenvalue, and eigenvector is the resultant vector, which also looks like matrix. Okay, um, yeah, so they have taken a very simple example 5 4 1 2, and vector is xy, and if you calculate a minus lambda I equals to 0, you will get lambda values are 6 and 1. Okay, these are your scaling factors basically. Intuition should be, if you see the lambda values, you should, in your mind, you should understand, okay, if I multiply uh, x and y, okay, um, whatever the vector is, if I multiply with these lambda values, okay, the transformation would be such that the values won't change, the actual values of x and y won't change. Okay, so these are your eigenvalues. And when you substitute 1 in the original equation, you will get, and do some transformation, you will get certain vector which is your eigenvector. Okay, this is the vector that doesn't change. Its only magnitude changes, but its actual direction or other things don't change, properties don't change, it retains the values. And likewise, if you replace substitute lambda is equal to 6 and do the transformation, you will get another vector which is 4 by 4 comma 1, and this vector also exhibits the same properties, wherein which it will also not change upon doing the transformation. You multiply a matrix to it, or you multiply a scalar value to it, it can only stretch, it doesn't change the direction. Okay, so that is what eigenvectors and eigenvalues are. Same thing is calculated for 3 by 3 matrix as well. For 3 by 3 matrix also, you can see two three eigen vectors exist, and three eigen values exist. Okay, so always remember, number of dimensions whatever you have, so many eigenvectors will be obtained, and so many eigenvalues will be obtained. Okay, so this is pretty much about it. Okay, if you have understood, then um, we are done. So any doubts in this concept?